All right, in this section, we're going to talk about how to solve problems that are sort of the opposite of standard maximization problems. And in this section, we're going to solve what's called standard minimization problems. And a standard minimization problem is where you're minimizing, like right here you can see we're minimizing this function, but all of your constraints are in the greater than form. So greater than or equal to. So anytime that you have a minimization problem where all your constraints are greater than or equal to, you can use what's called the dual method. And the dual method is where we convert the problem to its dual problem, and its dual problem will be a standard maximization problem. So actually all three of these examples, each one of these examples, since all of these are minimizing a constraint, minimizing the objective function with all the constraints are greater than or equal to, then each one of these can be solved using the dual method. Before I teach you how to use the dual method, I need to explain to you how to transpose a matrix. So all you have to do to transpose a matrix is, let's say I've given you this matrix here, A, and it's actually 3 rows by 3 columns. So all you do to transpose the matrix is you simply take the first row of the matrix and convert that to the first column. So notice I'll take the first row and I'll make it be the first column. And then you take the second row, so take the second row, and then you make it be the second column. And then you take the third row, so take the third row and make it be the third column. Okay, so basically you just convert this row to the first column, the second row becomes the second column, the third row becomes the third column, and so forth. And so that's how you find the transpose of a matrix. And the little t as an exponent represents the transpose of the matrix A. So here's another one. Notice here the first row is -2, -4, -24. So to transpose that, I would make the first column be -2, -4, -24. And the second row is -3, -3, -21. So I would make that the second column, -3, -3, -21. The third row is 4, 2, 20, so that would become my third column, 4, 2, 20. And then the last row, 3, 4, 1, would become the column 3, 4, 1. Now, it's not much consequence to you in this course, but I just thought I'd show you that if you transpose a transpose, it actually just gives you the matrix that you started with back. So for instance, let's say I took this matrix and I transposed it. So if I transpose this matrix, then the row 2, 3, -2 will become the first column 2, 3, -2, and the row 5, 1, 0 becomes the first column 5, 1, 0. Well, then if I took the transpose and applied the transpose to that, then this row 2, 5 would become the first column 2, 5. The row 3, 1 would become the next column 3, 1. And the row -2, 0 would become the next column. And notice that it just gave me back what I started with over here, the matrix A. So if you transpose the matrix twice, it just gives you back the original matrix. So what is the dual problem? Well, every standard minimization model can be written as a standard maximization model, and this standard maximization problem is called the dual problem. And it turns out that the optimal solution of the two models are the same value. Now when I say optimal solution, I'm only referring to the value of the objective function. In other words, whatever the minimum of the standard minimization problem is, it'll be the same as the maximum of the corresponding dual problem. Now the values of the decision variables are not the same values, but I'll show you how to deal with those later. So all I want to do here is show you how to set up the dual problem. We'll worry about solving the dual problem later, but let me show you how to find the dual problem. So let's say you start out with a standard minimization problem. Okay, so if you'll notice here, notice that you've got these two problem constraints, x1 plus 3x2 is greater than or equal to 15, and 2x1 plus x2 is greater than or equal to 20. And then you've got this objective function, but we're going to write this objective function in the other direction. So I'm going to write it as 5x1 plus 2x2 equals 1c. So I'm going to use 1 for c. Now, what I can do here is I can write what's called the coefficient matrix. So I just copy the coefficients of these. So the coefficient of the first inequality would be 1x1 and 3x2. So the coefficients here are 1 and 3. And then the constant here is 15. And then the second inequality, I get 2 and 1, and then the constant is 20. So I'll put 2, 1, 20 there. And then the objective function, the coefficients are 5 and 2. So I'll put 5 and 2 there. Now normally I just write a 1 here, but I put the C there so you could see that the 1 really stands for 1C, but you don't really have to put the C. Now, this is our coefficient matrix. Now, this is not a tableau, so don't think of this as a tableau. It's just a matrix that represents the coefficients of your constraints and the coefficients of your objective function. And notice I put x1, x2 up here so you'd know that these are the coefficients for x1 and these are the coefficients for x2. Now, to get the dual, what we're going to have to do is we're going to have to transpose this matrix. So we take this matrix and we transpose it, and then the row 1, 3, 15 becomes the column 1, 3, 15. The row 2, 1, 20 becomes the next column 2, 1, 20. And the row 5, 2, 1 becomes the next column 5, 2, 1. Now, when we transpose it, we need to actually change the variables. So we're going to change these variables. So instead of using x values, we're going to use y values, and that'll become clearer later. All right, and then also here, we're going to use a different variable here. We don't want to use c in our dual because we want to use a different value in our dual. Now, I'm going to use c for my original problem and p for my dual. But some problems might use z for the original problem and w for the dual or something like that. But I'm just going to use c and p. All right, now, once I transpose the coefficients, I get my dual problem from this. So the bottom row actually represents my new objective function. So my new objective function is going to be P equals 15y1 plus 20y2. Remember, these are y's. These are y's now. So 15y1 plus 20y2 equals P, and that's my objective function. And then these are going to be my constraints. So this is going to be y1 plus 2y2, and I'm going to write this less than or equal to 5. So y1 plus 2y2 is less than or equal to 5. And the other constraint would be 3y1 plus y2 is less than or equal to 2. So 3y1 plus y2 is less than or equal to 2. And then you go ahead and write down your non-negative constraints. Now, how did I know that my dual was maximized and that these were going to be less than constraints? Well, it's because that's what the dual is. The dual is just the opposite of your standard minimization problem. So your standard minimization problem is where you're minimizing with greater than constraints. So your dual must be the opposite. It must be maximizing where all your constraints are less than. And so anyway, this is the dual problem. Now I'll show you another example of setting up the dual here. So I'm just going to kind of jump down here to another example and setting up the dual, just so you've got some good practice on setting up the dual. Now, ignore the heading here. It says applying the dual, but we're not going to actually apply it. I just want to show you another example of how to set up the dual. So first of all, notice that I have a standard minimization problem here because I'm minimizing, and notice that both of my constraints here are greater than or equal to. Okay, so to write my coefficient matrix, I would look at my first constraint and I'd write 2, for the coefficient of x1, 1 for the coefficient of x2, and 5 for the coefficient of x3, and then 20 for the constant. My second constraint, 4, 1, 1, 30, because it's 4, 1, 1, 30. And then my objective function, the coefficients are 40, 12, and 40. So put 40, 12, 40, and then we'll put 1 there for 1c. So that's my coefficient matrix. Now transpose that, so I'll make the row 2, 1, 5, 20 be the first column, 2, 1, 5, 20. I'll make the next row 4, 1, 1, 30 be the second column, 4, 1, 1, 30. And then the last row, 40, 12, 41, that will be the last column. And so now this is my transpose. And from my transpose, I get the dual. Now remember, in your dual problem, the variables are y values. So these are y values. And remember, when you write the dual problem from this transpose, you're writing a standard maximization problem. So here's the dual problem over here. So I'm going to be maximizing, and then from the bottom row I get my objective function. 20y1 plus 30y2 equals p. So there's p equals 20y1 plus 30y2. And then from these rows up here, I get my less than constraints. So this would be 2y1 plus 4y2 is less than or equal to 40. So that's this constraint. And then this would be y1 plus y2 is less than or equal to 12. And that's this constraint. And then here I get 5y1 plus y2 is less than or equal to 40. And that's this constraint. And then don't forget your non-negative constraints. y1 and y2 must be greater than or equal to 0. Now, don't let it bother you that the dual problem here had only two decision variables, y1 and y2, and the original problem has three variables, x1, x2, and x3, because that's certainly possible. Because the number of decision variables that you have in the dual, they don't really have anything to do with the number of variables you have in the original problem. They actually have to do with how many constraints you have in the original problem. See, I have two problem constraints here, and so that means I'm going to have two variables in this problem, y1 and y2. So anyway, so don't freak out if you start with a minimization problem that has three variables, and then you get to the dual problem and you only have two variables, because that's definitely a possibility. Okay, so on the next example, next video, I'll show you how we go about solving this dual problem, because what we want to do is we want to solve this dual problem so that we can get the solution to our original a minimization problem that's up here. And I'll show you how to do that in the next video.